CC1020 Low-Power UHF Transceiver by Texas Instruments. Welcome to the training module on CC1020 Low-Power UHF Transceiver. This training module introduces CC1020 RF transceiver, internal configurations, and application considerations. CC1020 is a true single-chip UHF transceiver designed for very low power and very low voltage wireless applications. The circuit is mainly intended for industrial, scientific, and medical, and short-range device frequency bands at 402, 424, 426, 429, 433, 447, 449, 469, 868, and 915 MHz. It can easily be programmed for multi-channel operations at other frequencies in the range of 402 up to 470 and 804 up to 940 MHz range. With the CC1020, communication ranges can exceed 2,000 meters and data rates up to 153.6 kilobits can be supported by increasing the programmable IF bandwidth. The number of external components needed is very low, and the CC1020 requires no external RF filtering, IF filtering, or RF switch. The CC1020 is ideal for narrowband applications and perfect for battery operation systems requiring long range and good noise immunity. Typical applications for the CC1020 are one-way and two-way RF systems that require narrowband operations and a high data rate, automatic meter reading, alarm and security, remote keyless entry, tire pressure monitoring, and home automation systems are just a few of the many potential uses for the CC1020. A simplified block diagram of CC1020 is shown in the figure. The received RF signal is amplified by a low noise amplifier and down-converted in I and Q to the intermediate frequency. At intermediate frequency F, the IFQ signal is complex filtered and amplified, and then digitized by the ADCs. Automatic gain control, fine channel filtering, demodulation, and bit synchronization is performed digitally. CC1020 outputs the digital demodulated data on the DIO pin. In transmit mode, the synthesized RF frequency is fed directly to the power amplifier. The RF output is frequency shift keyed by the digital bit stream that is fed to the DIO pin. CC1020 can be configured to achieve optimum performance for different applications. Here we list the key parameters that can be programmed to the configurable registers. In the next few pages, we will go through them in detail. In a typical system, CC1020 is interfaced to a microcontroller. This microcontroller is able to configure the CC1020 via a simple 4-wire SPI-compatible interface where CC1020 is the slave. The CC1020 can be easily interfaced with any microcontroller on the market. The only requirement is to have enough I/O pins. To configure the CC1020, 4 I/O pins are required. The microcontroller interface is shown in the figure. The pins connected to PDI, PDO, and PCLK can be shared with other circuitry, provided these circuits are not active when the configuration interface is active. One I/O pin can be saved if PDI and PDO are connected together, and a bidirectional pin is used at the microcontroller. The PSEL signal must be driven by a pin dedicated only to interface to the CC1020. For data interface, 2 I/O pins are required, one bidirectional for DIO and one input for DCLK. Optionally, one microcontroller pin can be used to monitor the lock signal. This signal is at logic level when the PLL is in lock. It can also be used for carrier sense and to monitor the internal test signals. The data rate is programmable and depends on the crystal frequency and the programming of the clock registers. The baud rate can be calculated by the equation, where div1 and div2 are given by the value of MCLK div1 and MCLK div2. Any data rates up to 153.6 kilobaud can be configured. There are 2 frequency word registers, termed frequency A and frequency B, which can be programmed to 2 different frequencies. One of the frequency words can be used for RX and the other for TX in order to be able to switch very fast between RX mode and TX mode. They can also be used for RX at 2 different channels. In order to meet different channel spacing requirements, the receiver channel filter bandwidth is programmable. It can be programmed from 9.6 to 307.2 kHz. The signal bandwidth must be smaller than available receiver channel filter bandwidth. The receiver sensitivity depends on the channel filter bandwidth data rate, data format, FSK frequency separation, and the RF frequency. Receive signal strength indicator, giving a digital value that can be read from the RSSI register. The carrier sense signal is based on the RSSI value and a programmable threshold. The carrier sense function can be used to simplify the implementation of a carrier sense multiple access medium access control. CC1020 has a built-in automatic power-up sequence state machine. By setting the CC1020 into this mode, the receiver can be powered up automatically by a wake-up signal and will then check for carrier signals. This feature allows the host controller to wake up the radio and check for a carrier by toggling a single I/O line. The CC1020 requires a specific set of actions to take place before it will enter automatic power-up sequencing mode. First, the CC1020 must be calibrated. Second, the CC1020 should be put into power down mode 0. Finally, the CC1020 can be placed in automatic power sequencing mode and then enabled. The triggering of the automatic power-up sequencing can be accomplished by toggling the PSEL pin or simply by writing a register. When designing the impedance matching network for the CC1020, the circuit must be matched correctly at the harmonic frequencies as well as the fundamental tone. A recommended matching network is shown in the figure. The component values for various frequencies can be found using SmartRF Studio software. The use of an external TR switch reduces current consumption in TX for high output power levels and improves the sensitivity in RX. The external TR switch can be omitted in certain applications, but performance will then be degraded. L1 and C1 are the input match for the receiver. L2 and C3 are used to match the transmitter. Very few components are required for the operation of CC1020. The recommended application circuit is shown in the figure. The input or output matching network is introduced in the last page. It makes it possible to connect the input and output together and match the CC1020 to 50 ohm in both RX and TX mode. The precision bias resistor R1 is used to set an accurate bias current. The loop filter consists of two resistors, R2 and R3, and three capacitors, C6 through C8. C7 and C8 may be omitted in applications where high loop bandwidth is desired. An external crystal with two loading capacitors, C4 and C5, is used for the crystal oscillator. The CC1020 can be used together with various types of antennas. The most common antenna for short-range communication are monopole, helical, and loop antennas. Monopole antennas are resonant antennas with a length corresponding to 1/4 of the electrical wavelength. They are very easy to design and can be implemented simply as a piece of wire or even integrated onto the PC board. Helical antennas can be thought of as a combination of a monopole and a loop antenna. They are a good compromise in size-critical applications. Loop antennas are easy to integrate into the PC board, but are less effective due to the difficult impedance matching because of their very low radiation resistance.